welcome back. So let's continue on engineering units review here. Okay. So the table given here is pretty much the only units we're going to use in aerodynamics. So let's talk about a few things. Pressure. So in English engineering system, EES, like I said, this is US customary. This is SI. Okay, so pressure is, pressure here, sorry. So the standard unit of pressure of EES, English engineering system, is of course pound force feet square. Let's call this PSF, pound per square foot. Okay. SI unit, of course, Newton per meter square. This is called Pascal. Okay, those are standard. Now, oftentimes people use non-standard units. For example, pound force per inch square. So this is a PSI, pound per square inch. This is a massively non-standard unit. So oftentimes PSI is given, you have to convert back to PSF. Conversion here is 1 PSI is of course 12 square PSF. In other words, this 12 square is 144. Okay. Reason why people want to use PSI is PSI will give you a nicer unit, which is standard serial atmospheric value is 14.7 psi, but if you use PSF, 2,116 PSF. People want to use 14.7 instead of 2,116. Okay, so that's why. Okay. Here, density. Which is P. Density. Density is rho. Greek lowercase. Standard unit is of course rads per cubic foot. Now in typically thermodynamics, this is oftentimes given by pound mass per inch cube, which is horrible non-standard unit. The reason is of course this is going to give you a much nicer number, that's why. So be careful, this is such a non-standard unit, you have to convert everything to Srag and foot. Okay. SI unit, obviously standard is kilogram per cubic meters. Okay. Pressure, density, temperature. Temperature is, of course, Rankine current. Gas constant. This is aerodynamics, so we are going to only pretty much using gas constant of standard air. Okay. So this is oftentimes called specific gas constant because it's specific only to air. So if you're talking about standard air, gas constant is 1716. Unit is foot pound by Srag Rankine. This is 287, of course, Newton meter, kilogram. Okay. This Newton meter is called joule. Okay. So those are pretty much the units we're going to use: pressure, density, gas constant, temperature. There are a few things. This is the conversion between relative scale to absolute scale temperature. Okay. 1 atm, this is the standard suitable atmospheric pressure, which is 14.7 psi. Let me just write it down here. Okay. 1 atm, 14.7 psi, or 2116 psf. Either way. Okay. ATM for SI unit is oftentimes called 101 kilopascal, or oftentimes called 1 bar. Okay, that's 1 ATM. Okay. Also, other things, the conversion between SI to US customer unit for the banks, feet to meters, and this is the force, pound force to newtons. This is the banks, 1 mile to feet, 1 hour to 3,600 seconds. Now this is the very, very convenient conversion from miles per hour to feet per second, because oftentimes feet and second, those are standard units. So you have to convert quickly from miles per hour to feet per second. You can use this conversion. All right, next page. Okay, so now, flow field representations. Let's take a look at the video for a moment. Okay. So I want to show you a video called Smoke Wind Tunnel. So this is a flow visualization type of wind tunnel testing. So here is the test section. Side door is open. You're going to attach a model. You're going to close the door. Then you see a bunch of smoke streaks coming in. So those are the lines created by a smoke particles. So upstream of this wind tunnel, you have a wire. That wire is heated up, and then you're going to drop the oil. That oil is burned, and then creating small tiny smoke particles. And that is going to be continuously provided to the flow field, so that you can visualize the flow field. This is called smoke wind tunnel. So you can take a look at the flow field by looking at this line. Let's just go back to try to go ahead. Okay, so I just posed. So as you can see, the lines are very nicely defined around here. Okay. So those are the lines created by smoke particles, which is essentially called streak lines. Continuous injection. So this is called streak lines. All right. Now, obviously at the same time, if you want to keep your eyes, suppose if you zoom really in, and then take a look at a single particle, and then if you keep track of the motion of that single tiny particle, starting from here all the way to the end, that is oftentimes called path line. This is the path of a single particle. A big difference between path line and streak lines. Streak lines are created by many particles. It's just the particles are released at the single location and then continuously released at that point. So a flow field basically creates the streak of that particles. Path line is an independent individual particles. Okay, so if the flow is steady, what do you mean steady? If the flow is steady, those two are essentially the same thing. So that's the essential definition of steady flow field. Steady flow field is the flow field which is time independent. regions of not the steady flow field in this picture also. Suppose if you look at around, the area around here, you don't see any lines, or you can see lines, but it's not like lines here. It's more like random, chaotic, and then it's not like creating a very crystal clear defined lines. So those are the regions which is not the steady. If flow is not steady, you cannot create streak line, okay? You cannot do that. Obviously, the streak lines cut off and then become smooth. It's like a very random chaotic region. You can possibly keep track of the individual particles' paths, because those are essentially, you're seeing lots of individual particles moving just randomly and creating big wide region of turbulent flow, which is essentially called the wake region. So path line can still be defined. However, path line usually cannot tell you the overall figures of the flow field. Okay. So aerodynamics, we are going to focus our eyes on the steady flow field. If flow is steady, okay, obviously if the flow is steady, we can define both streak lines and the path line at the same time. Okay, and also another reason of why steady flow is so useful, we can mathematically represent these lines. Lines means streak line and path line. Because essentially, these are the same. Okay, important thing is, this is the concept of streamline. Obviously, if the flow is not steady, you can define such a thing. So this only exists if the flow field is steady flow. Okay. So in terms of physics, streamline actually also represent, this is a line in a flow field. That everywhere along this line, velocity is tangent. That's actually physical meaning of also the streamline. So by seeing the streamline, in this case, you're seeing a bunch of streamlines. So this is, in essence, streak lines slash path line, but at the same time, this is also streamline. So along this path, you can actually tell the direction of the velocity at each location along this path, or this line. It's always tangent direction. Okay? So that's the streamline. That's quite important because later on in this class, we are going to pick up the concept of streamline, applying some mathematical analysis to come up with certain equations so that we can use to solve the flow field. Okay? All right. So as you can see, this is a smoke wind tunnel. Those are the streak lines, but at the same time, this is steady flow, so this is the path line at the same time, streamline also. Streamline, streamline. This is obviously not the streamline around here because it's not steady flow. So through the element, small tiny piece of air is going to flow along this path called streamer. Okay. Now, if we include the viscosity, that actually creates the boundary layer. Boundary layer creates the velocity difference between location 1 to 2 over the perpendicular distance away from the surface dy. This is called the boundary layer. If the boundary layer exists, of course, you can determine how much shear stress you're going to develop between two different locations by taking Newtonian viscosity-based shear stress model, in which we covered already in fluid mechanics. Now, in aerodynamics, typically we are going to completely ignore this. It's called inviscid flow. Okay? If we include this, in other words this, it's called viscous flow. All right. So here is the flow field. We want to represent the flow field typically using pressure, density, temperature, velocity at each location. And then oftentimes we're going to talk about the inverse of density called specific volume to represent also how much volume change happens for a given mass within a given flow field. Okay. So next page. Let's take a look at the equation of state. Of course, in Aero1, we oftentimes assume that the air behaves as ideal gas. If the gas is ideal gas, of course air is a gas, it is going to follow a certain rule. It's called equation of state for ideal gas. Okay. Of course, we have two different types of ideal gas. One is something called thermally perfect ideal gas. One is calorically perfect ideal gas. This is true in wide range of temperature. And wide range of temperature means that true in subsonic, supersonic. Okay. We are going to take a look at what it really means later on. Not now. So we're going to find out a little bit more details. This one is true only in rule of thumb is room temperature range. So true only typically subsonic flows. Okay. So in order to more crystal clearly define this thing, is we need to introduce the concept of specific heat. A flow field property called specific heat is not the constant. This one is specific heat. Is actually constant. So that's going to make a big difference. Now, even though this is not the constant, we can still model it. can be modeled in terms of temperature. So we can still model specific heat in terms of temperature, so we can still treat the gas as an ideal gas. But it's a different type of ideal gas, so we have to move on with caution. This one is much more simple in terms of mathematics. So this is two different types of ideal gas, but either way, we can apply ideal gas equation of state, which is very simple equation, P equal to rho RT. Okay. Important thing about that, of course, this one is a specific gas constant. Specific gas constant, we looked at it already. This is a 287 joule per kilogram K, or 1716 foot-pound per slug Rankine for air. So 287 joule per kilogram K, or 1716 foot-pound slug Rankine. Okay, specific gas constant for standard air. Also, another important thing, if you're talking about pressure here, this must be absolute pressure. Very common mistake is do not use gauge pressure. Very, very common mistake. People use gauge pressure here. Get the wrong value. Temperature, again, similarly speaking, this is going to be absolute temperature. What do you mean? Do not use relative scale. Do not use degrees F. Do not use degrees C. Okay? Absolute scale means Kelvin or Rankine. So this is called equation state. Let's move on to the next page. Let's take a look at this example problem. Let's look at a very simple example problem. The air is flowing on the wing of Boeing 787. This is the cruising condition. The pressure and density of air measured was 3.25 psi absolute and 0.00075 slugs per cubic foot. What is the temperature of air at that point? Okay. So pressure is given. This is given as absolute pressure, 3.25 pounds per inch square psi. So let's convert it. How do you convert it? 1 foot over 12 inch. This thing squared. This actually making this is 144. So 144 times 3.25 gives you 468 pound feet square. This is PSF. This is a standard unit. Density is given 0.00075 slug per cubic feet. This is a standard unit. So we're going to plug into P equal to rho RT. We are going to find out temperature. Temperature is equal to P over rho R. Pressure is 468. This is pounds feet square. Density 0.00075 slugs per cubic foot. Gas constant 1716 per pound slug Rankine. Computing all of these, you're going to get temperature, which is 363.63 Rankine. This is not N, because the program is asking you what is the temperature in degrees F, so you have to actually convert it. Temperature in F is 363.63 Rankine. Subtract 460, which is minus 96.37 degrees F. Okay. So that is the end of unit A1. Let's stop.